Hey everybody, welcome back to another video lesson. Today we're going to go ahead and take a look at solution equilibrium. So we're going to apply the principles of equilibrium to the formation of various solutions. So to get started, let's go ahead and take a look at an example. So what we're going to do is we're going to take some solid calcium phosphate. So we're going to take solid CaPO4. I'm going to drop this into a solution of water, and we're going to have this dissolve. Okay, so when this dissolves, what happens is we get these ions in solution, and the ions that we end up having in solution are those calcium 2+ ions, and we get those phosphate ions. Now, since this is dissolving in water, what's going to happen is it's going to dissociate into various ions. And we're going to have these ions that are floating around in the solution, but what happens is we can only put a certain number of ions in solution before they start to build up and form the solid at the bottom. And that's what's happening here when we make the solution. So when we get to this point, when we get to a point where we create a saturated solution, where we can no longer put any more ions in solution, these ions are going to start to form into the solid phase, and then that solid phase is going to break back down into the various ions. So what we're establishing when we create a saturated solution is an equilibrium system. So this is going to constantly be bouncing back and forth between the solid phase and the ion phase. Now, you don't necessarily have to see the solid for it to get there. You just need the solution to be saturated. So you can have just a trace small amount of ions in solution that you can't see with your eyes, and it would still be considered at equilibrium. So we want to make sure that when we're dealing with solutions that we have reached the saturation point. So when you're looking at calculations or doing problems with solution equilibrium, just make sure that the solution has reached saturation. Okay, if they tell you that in the problem, then you're good. Now, the amount of solid that's left over doesn't really matter. You can have a lot of solid left over, you can have a little bit of solid, or just a negligible amount that you can't even see. All of those would indicate that the solution has to be saturated. So keep in mind that it has to have the maximum amount of ions in solution. If it does, then we can go ahead and write our equilibrium. So we can write the equation just like I have here already, and then we can write our equilibrium expression. All the rules and principles that we established back in equilibrium are going to still be present here. We're still going to follow the same idea that this is an equilibrium constant that will not change unless you change temperature. We don't write solids or liquids in the expression. We only put the aqueous and liquids. So therefore, when we write our KSPs, it's always going to be products, and there ain't going to be, there's no division. So essentially, you're going to take your products, which are on the top, and your reactants are always going to drop out because you have a solid. Now, one little note about dealing with solution equilibrium is it's a good idea to always write it with the solid on the left and the ions on the right, even if you're starting with ions in solution. So we're going to see problems where we have ions in solution. We want to see, will it precipitate out and form a solid? So will the reaction shift to the left or favor the left, or will it favor the right? So either way, just keep the reaction written this way so that you always get a KSP, so it's multiplication, so that there's no division. That's why they call it a solubility product. Okay, so just like all the other KSPs, it's only going to depend on the concentration of the ions, not the amount of solids. And the, I think I already mentioned that, saturated solution, and okay, so just like we saw with K's before, what the KSP is going to give us information about is the degree at which this solid will dissolve. So again, if KSP is high, if there's a large value for this, that means that there are a lot of ions in solution. So a high KSP, when your KSP is large, that means that there's many ions in solution. So therefore, you would assume that this is a pretty good, let me rewrite that there, this is a pretty good solution, that this is going to form a lot of ions, that it will dissolve readily in the water. So many ions are formed. If it's going to have a low KSP, then you're going to have a not very soluble substance. Now, I didn't write it in here, but the KSP for the calcium phosphate is actually a very, 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 very small number, so therefore this isn't really going to be soluble. They're not very soluble at all. So what that means is if I put the solid chunk in there, just a small amount of ions are going to go in solution, and then they're going to right away start to form back that solid. So therefore we're going to favor the solid formation. And what that also tells me is that if I put a lot of calcium and phosphate ions in the solution, it's going to quickly come together to make a solid. So therefore, it's going to be readily precipitating the solution out of the solution. So again, keep in mind how we dealt with K before. High Ks favoring the product. Low Ks favoring the reactants. Okay? So one other thing I need to mention, since I'm kind of making a lot of connections here between KSP and solubility, is it's not directly, it's not KSP is not solubility, is what I'm trying to say. So there is a relationship there, but they're not exactly the same thing. So be careful with this. So solubility is essentially how much solid is going to dissolve to make the solution saturated. The units that we always use for solubility are molarities, or sometimes you use these grams per liter or per milliliter, depending on the scenario. But essentially, it's about how much is dissolved into a volume of solution. When we're dealing with KSPs, remember KSP is an equilibrium constant and there are no units. So right away that should tell you that these are not exactly the same thing. But there's a connection and there's a way we can look at, and we'll look at some examples in later videos on how these two are related to each other. But the idea is that they're not the same thing, so be careful with that. So the solubility can actually change if we change some parameters of the solution. Like I could add other things in here and I could change the solubility, I could change it, the pH, I could do various things to change the solubility, but the KSP will not change, because KSP is only going to change if you change temperature, just like all the other Ks that we've been dealing with all year long. So that should be a good, good start with at least the general background of what KSP is and how we use it. And in the other videos, I'm going to show you how we actually do the calculations. So thanks.